こんにちは。Hello. Hello. Today, I would like to talk about the how to estimate the nonlinear term. Okay. Anyway, we are consider the free boundary problem for Navier-Stokes equation. Problem. Navier-Stokes equation. And then we use the Lagrangian transformation. And EYT, UYT, velocity field, and pressure field. Lagrangian coordinate. Y. This is coordinate for the reference body on t time. And then we have the nonlinear equation dt b minus divergence mu dv minus qi is equal to v omega t, and divergence b is equal to g v is equal to divergence fold v in omega t, and the boundary condition is mu dv I n is d v gamma t, and then initial data, initial condition in omega. So this is we get after Lagrangian coordinate. And then here is nonlinear term, and nonlinear term is essentially have the k b, I write b, and dtb plus some function kb, no, sorry. Yes, k0 nabla kb, second derivative of no, sorry, no, kb, here is kb, of second derivative of b plus nabla k b, and first derivative of nabla b, and kb is 0 to t gradient b ds. It's come from the Lagrangian. This is f, because we use the Lagrangian transformation y plus 0 t b ds. Therefore, nabla x, the derivative with respect to x becomes the derivative nabla derivative with respect to y plus some function, nonlinear function over here, this k y, and K is present. So we have this. Therefore, from this transformation, you get these nonlinear equations. And so, okay. And then FB is this one, and the GB have the form of K. K, some function K0 B, K, B, blah, B, and board V, G is also the some function of board G0, KB, and B. And B also some function B0, KB. This is not the exact formula, but anyway, the main terms is this. This is the formula of nonlinear terms. Then today, okay, so then we use to solve the equation at least locally in time. Time. The Banach's fixed point. Argument. This is the standard. Namely, symbolically, if you write the problem is A equal B. Okay, so it's a different F. You want to solve this problem. Then, first of all, you have to define some underlying space X, and then you choose X for any U from X. You solve linear equation U. Oh, of course, with the initial data, but now I don't write it. Just rough idea. Then, okay, so you get a map from U to V. So from this, you get a map phi U to V. And then what you have to prove is that one is phi is X at least into X. Phi is defined on X and map into X. The second is that phi is contraction. Namely, there exists some C positive but less than 1, such that for any U1, U2, X, Y U1, and Y U2, norm X norm is less than constant C 1 minus U. You have to prove these two assertions. Okay. Then, of course, the Banach fixed point argument, fixed point theorem tells you that there is a unique U in X. This is a fixed point. U for U. So obviously, this U is a solution to this equation. dtu, sorry. dtu minus U. U is a solution of this equation. This is a very, very much classical argument, but anyway, one of the standard arguments. At least to prove the local in time, unique existence of local in time solutions. Unique existence. And the uniqueness is guarantees the uniqueness of the fixed point. Therefore, whenever you use the Banach fixed point argument, the uniqueness is automatically followed. Okay. Then, what is the problem? What is first? We have to define X. And then, secondly, how to prove the existence of C. So usually, C is, you can get C is some kind of constant times T to the minus some power. Some powers. Okay. So fixed point time dependent problem case is this constant C is the usually some constant independent constant independent of time T, and then some time power sigma. Sigma is positive power. Therefore, T is very small. Then C, you can choose C is less than 1. Or in other words, you choose chapter T in such a way that small c is less than 1. So this is the standard method. And of course, this estimate come from the linear estimate for the equations. Okay. So this is standard argument. Therefore, okay. Then the first task is X, underline space X. And then in this case, in our case, okay, so let's say xt here, and then u, lp, lt, x to q, omega, intersection, lq, omega. Standard our solution class. And then the requirement is initial data, t equals 0, is our initial data, V0. And energy of U. Now energy is this. So U LP 0T omega norm plus ETU LP 0T LP omega. So energy is this one. It's finite or some maybe it's not necessary to say, but anyway, some omega. So energy is also in some sense, each iteration, energy is some less than some fixed constant. And then, moreover, important assumption is that we have to always we have to define the Lagrangian coordinate, and therefore we need the assumption that grad u at infinity norm ds less than delta naught. As I said, that to solve the equation, always this kind of smallness assumption is assumed. This smallness assumption guarantees that the Lagrangian map is one-to-one. So we need this assumption. So we are looking for the solution which satisfies this assumption. Yeah. Then linear estimate. Okay, now we are follow our story. Then okay, so we now take u from xt. Then our equation is dt d minus d b minus qi equal to fu omega cross 30, and the divergence d is equal to g u is equal to bold u. It's in omega cross 0t, and the new dv minus qi n is equal to b u on gamma 0t, and the initial data bt equals 0 is equal to b0. This is our linearized equation. Yeah, namely this one, this part. I'm sorry. This is b. No, this. Our x is this. And then our equation, linear equation, is this. Yeah. So then first we show the map phi is defined x. Map phi the maps x into x. Yeah. But anyway, we use linear estimate. Already I write, but important point is that in order to get linear estimate, first we extend the right hand side is to whole time, because my theory is that deeply depend on R bounded. theory. Therefore, always use Laplace transform to construct a solution. Therefore, we have to, in order to use the Laplace transform in time, of course, we need that the f right hand side that defined for all time. Okay. Anyway, and also in order to prove one is just we estimate this one, but to show that the second, we have to consider u1 minus fu2. So this is like k u1 u1t u1 minus ku2 u2, etc. So this term is, of course, you know that u1 plus u2 u1 minus u2. This kind of, you use this kind of trick. Right? Therefore, okay, and therefore, the two nonlinear term, usually we consider every, it's independent of this p. Just now, I would like to talk about how to estimate the right-hand side, right? Nonlinear term. And then, of course, Ku, we have to estimate K, not only Fu, but anyway, Fu, and also this kind of difference. Therefore, for convenient, we consider the dtu plus, for example, F case is Kb dtu, and then, sorry, F0 Kb, second derivative u, and nabla Kb, nabla u. For example, to treat not only f of u, but also this difference, I would like to estimate this term. Finally, this corresponding this one or this one. Right? Okay. And then for f, what we have to estimate is just that f LP extension of f is we estimate this one. This one. Meaning is that there is no derivative in time. Of course, x also, but especially derivative in time. Therefore, LP norm, in this case, the extension is very simple. Just zero extension is enough. Right? F0 is a zero extension. Zero extension. Problem is if you have the estimate, nonlinear term have the time derivative. In that case, extension is much more complicated, but the only LP norm in time. This case is extension is just a zero extension. Okay. So this one, and then F0 is of course from this. Sorry, we need e to the minus t. Excuse me. We need something here. This weight. Excuse me. But anyway, but this is just e to the minus gamma t p r q omega. Sorry, 0t. And e to the minus gamma t is decreasing function. Therefore, when t range on 0 to t, this is really to say. It's equal to so the right hand side f only what we have to do is just estimate this one f. Okay, it's simple. Then I assume that this is larger than n. N is a space dimension. The reason why I want to use the algebra for h1 to omega, meaning is that uv, if you take two function from h1 to, then you have h1 to norm of this sometimes u h1 to the h1 to. Yeah, of course, there are many arguments to relax the condition for Q, but our program is a so-called quasi-linear program. I don't know that how to relax this condition. Anyway, how use this condition is just I want to use this algebra of H1Q. Moreover, I mean U L infinity norm we call sometimes U H1Q. This is so-called Sobolev embedding theorem. This is essential, our essential point of our argument. So whenever Q is greater than dimension, you have this. Okay. All right. Then how to estimate F? So first, KV DTU goes to the LQ norm. Then this is KV. DTU is belongs to LQ. Therefore, okay. So this LQ norm is going to this one, and then you have to use L infinity norm of this one. Right? You take the LQ norm of this product, but then DTU is for each DTU belongs to LQ. Yeah. If you remember the space, our space U for U is I'm sorry, 0P2, LQ, intersection LP, LT, H2Q. So time derivative DTU belongs to LQ. For each T, I mean, for almost every T, DTU belongs to LQ in space. So you have to use the LQ norm for DTU. So this is the best, in some sense, best estimate, right? And then the KB is what? 0T WVS. Therefore, KB L infinity in cos 0T log V is L infinity ds. And then T is also range from 0 to T, so you can maximize so this. And then you use this. So constant times 0T to V leads to H2Q. Yes, right? Nabla V L infinity norm is estimated by gradient V H1Q from this Sobolev embedding, Sobolev inequality. The gradient U H1Q norm is a second derivative, H2Q norm. Then, moreover, now we use, I say that we need some T to the power. From this, you get this T to the power. Meaning is that now we use Herder inequality. So Herder inequality here, 1 times this consider. Then d dt 1 over p prime under 0t, second derivative of s h2q p yes and p. Therefore, you get the c to the power times the p prime. And then this is energy of. Okay, now we can say that this is EV. Yeah. Say, could you please remember that E, B or EU is B, LP, 0T, H2Q plus B, LP, NQ. This is norm. Therefore, this is what? So H2Q norm of B, the LP in time. So this is if you use this notation, then this can be written in B, LP, 0T, H2Q. This norm. Yeah. Okay. So So summing up, so K D U Q norm, this is estimated by constant times T to the power P prime, and then energy V plus dTU T. Okay. So next, we consider some F0 V times second derivative of U. This is essentially the same because F0 is like if you use the Taylor expansion, then you can write this is F1 theta V and yeah, KV is essentially the node. So you may assume that this term this is constant because F0 is a constant. Sorry, function. F0 is a function C infinity function defined on is less than delta naught, and then 0 is equal to 0. So nonlinear term, but essentially, it's essentially you may forget this term, and then essentially this term is this one. Therefore, also the same as this memory. Of C, constant come from here, and then then also this second derivative of U is just LQ, right? So here U is also it's also. You maximally you can use LQ norm of this one. Therefore, you write B L inf the second derivative of U LQ. It's the same as the DTU case. So it's really how T to the point. So this can be estimated P prime P. Okay. second derivative of u LP. It's the same as this one. It's easy. And this third term. Now it's with third term. This is exactly 30. Second derivative of v is yes. First derivative u. Therefore, now we take LQ norm of this one. Then now we take LQ norm here. But in this case, second derivative of b you have. Therefore, you have to use LQ norm, this one. Therefore, 0t, second derivative of b is LQ norm. Yes. And then gradient. You have infinity norm of this. Then, okay. Then, okay, this is also the giant 0t, the same. The dual, you have this, and then this term, to estimate this term, you use Herda inequality. So you get this one. And then this time you use the over inequality. It's on Q. Therefore, okay. Then we now we take LP norm in time. Now we take LP norm in time. Yeah. Then here is. Okay, so you take LP norm in time. Then T is here only. So constant times T to the P prime ED. And then this one, so dt to LP in LP Second terms is this one. And this is also only the t variables here. So you take LP norm in this. So t to the minus b. And then second derivative, so u. And then thirdly, you have the third terms is this one. This is estimated by this. And the time derivatives, time variables here. Then you can take the LP norm with this one. So this is, you say, number of LP is EB. This one, Q. So second, LQ norm second derivative U is H to Q, H to Q, and first derivative H1 Q norm of first derivative U is also H to Q. Therefore you have T to the minus power P prime UB. You have this. Then we get to F T to the minus gamma T 0. You have this as okay. Now I will consider the denoted estimate for the G U. But now, as the same reason, instead of G of U, I consider the K G0, KB, and W. And also G of U, instead of G of U, the same reason, I will consider G0, KB, U, and boundary data, PU. So we have the B, some B0, KB, Nabla, U. So it's the same, in some sense, same. And then what we have to estimate is that, okay, if we use the distance, then what we have to estimate is first we define some extension, and then we take the e to the minus gamma t norm of this, of h1 half p r q plus e to the minus gamma t gu e lp r lq. we so we are but so and then here is h1/2 derivative. So it is not good. If we use the zero extension, then this is not good because of h1/2 derivative here. So you have to consider the different extension because of this derivative. Of course, for this case, this is just only LP in time. Therefore, it's a zero extension is okay, but h1/2 p, this case is it's not good. And also, BU and this GU and BU is the same. This is BU and also same. Then it's board of U. We need GT or some suitable extension of board of U, board of G of U. And then we take H1T. Oh. Therefore, now board G of U, then you have to use that first derivative of time. Therefore, extension also you have to consider this time derivative. So zero extension is not good because if you use the zero extension, then first derivative have singularity. Okay. So maybe so first I want to talk about the extension. Okay. So extension. So first, if f is a function, it's a function defined on 0t, and if f satisfies 0 at t equals 0, this case is in some sense zero extension is okay for derivative. I mean, in this case, our extension is the following: if 0, t is negative, and then ft, t, capital T, and then when capital 2t minus t, when t is greater than t to the 2t, and then 0, other than 2t. This is some kind of standard extension. When t equals f satisfies this condition, when f satisfies this condition, vanishes at t equals 0, then extension of f is defined in this way. So t negative, then 0. So 0 extension. And then ft, when t is just in this interval, then ft. Then t equals 0 is integral, the differentiable because of this condition. And then after t is greater than capital T, then you say, I don't know in English, it's in Japanese it's orikaishi. So how to say orikaishi? A reflection. Reflection, yes. So reflection. Yeah. So when chapter t equal t, just this is coincide these two terms. And then when t equal to t, this become to 0. Yeah. So it's of course continuously connected. And then when t equal chapter 2t, again this is 0. Therefore, 0 extension is also differential. So this is good. So in this case, dt to f v is of course 0 for t negative, and then f prime t for 0 to t. And then in this here, minus. Of course, this time derivative is a distribution sense, but almost everywhere you get this one. Distribution sense means that dt e of f, then you get here is test function. You take for any c0 infinity r, and then you consider the distribution derivative means that you consider this one. And then, of course, yeah, then you are okay. So sorry, you have to divide the interval 4 parts, 0 to minus 2, 0 to t, to t to 2t, plus 2t, plus chapter to infinity. Yeah. And then you make integration by parts. Yeah. You make integration by parts. Then dt, for example, t equals 0, this becomes 0. So you don't get so integration by parts, you get just infinity 0 to minus ef dt pi dt, right? Integration by parts, right? There is also integration by parts. No, sorry, 2t. I'm sorry. Excuse me. End point 0 and 2t, this vanishes. End point, right? End point t equals 0, this is 0, and t equals 2t, this is 0. Therefore, if t vanishes at t equals 0 and t equals 2t. So integration by parts, you get t to 0 to 2t, also e to f dt phi dt. And the same reason, final part also you have. Oh, sorry. Therefore, in this way, you can show that this is equal to r e f dt phi dt. This means that distributional derivative with respect to time t is just the same as this one. Meaning that this. Okay. So anyway, from this observation, extension of G0 KB is of course KB equals 0 is equal 0 because kb is 0 to t to nabla b ds. Therefore, t equals 0 is equal to 0, right? So extension of kb is this use this one. But nabla u does not vanishes at t equals 0. Therefore, we need the different extension. So I don't know. Maybe my method is not only the method. I think maybe there are several different ones. But I prefer to use the following method. First, namely, I want to use the semi-group continuous semi-group generated. Okay, let's say T. Sorry. Why I use capital T to represent the continuous analytic semi-group? I don't know the reason, but this is my custom. Capital T. Anyway, this analytic semi-group is associated with Stokes problem. The Stokes problem. Problem W minus T minus. Okay, PI. Zero. I got this W zero. And then boundary condition. Boundary equals 0. This is in omega. Omega equals 0. This is boundary condition. And then, of course, the pressure P exists. Therefore, it's not a semi-group setting. But maybe I already told you that we, according to the group Solonikov method, following the group Solonikov method, we eliminate P by using the divergence W. I already talked about this one. I don't remember. Stokes problem. Stokes problem case is you know that group Solonikov. Maybe not so. They consider more very much general Stokes equation, very much general boundary conditions. But point to say to show that the generation of analytic semigroup P has no time evolution. Therefore, we have to eliminate P. This is one of the characters of Stokes equations. But anyway, how to eliminate P is usually we solve. Let's consider W with Dirichlet problem. Usually now under this condition, with Dirichlet problem, we consider the U boundary condition. Boundary condition is equal to dU, but it's now 0. Maybe this is okay. And then let's say this is k, functional of k. And then the corresponding problem is this one. On the boundary condition. This is a way to eliminate the pressure P. Meaning that I think maybe today I do not want to explain why the equivalent of this problem and this problem. But in order to eliminate P, you consider this weak Dirichlet problem. This is for 85. And you solve this weak Dirichlet problem. But it's a general domain. You cannot solve this weak Dirichlet problem. Therefore, we assume this weak Dirichlet problem uniquely solved. Then you can eliminate pressure P in this way. So this equation and this equation is equivalent, meaning that if you can solve this equation, then you put this is pressure P. If you put P, if you prove that the existence of this solution, then you automatically can prove divergence B equals W equals 0. Then you take pressure P, this one, right? On the other hand, of course, if you solve this equation, then the P is coincide with this KW. In this way, you can show that this problem and this problem is equivalent. Maybe already I explained. This is one of the important points to consider the Stokes equations. Okay. Anyway, maybe. Okay. Anyway, please believe that you can construct the analytic semi-group associated with the Stokes problem of this one. Then instead of U, we consider T 0. This satisfies T equals 0 is equal to 0 because U T equals 0 is B 0. Right? This is assumption for U. Right? U. So this satisfies. Therefore, you applied this extension for this one. But it's not to coincide with U. So therefore, you B0. These functions are defined for all T. I mean, okay, so excuse me. Anyway, rough idea is you consider this one extension for U is this one because at least 0 to T, this part becomes to this one, and the plus T of U0, therefore this really becomes to U. This term. And then this term becomes to 0 at T equals 0, so it's a nice extension. In some sense, 0 extension. Yeah. The plus this one. But T0 is only defined for T positive. Therefore, instead of T, we consider T just the even extension, B0. Even extension. This is differential. Once you can differentiate this once at t equals 0. So even. And then moreover, maybe it's better to use a cutoff function because I don't want to consider the negative t. Therefore, this is extension for you. Extension for you. Sorry. Extension. Here, IT infinity function. T is 0, so it's 2 and 4. Minus 2, sorry, minus 1. So we cut the negative t. Because we don't need the information from negative t a lot. So this is extension. And of course, you. And okay. And also, we need one lemma. Maybe lemma. Is what is which one? This is continuous. Of course, we need P and omega is C1 domain. Continuous inclusion means that for any u, it's 1/2 PR Q, it's 1/2 P R LQ distributed by constant U minus 1 Q plus Q LQ or H1Q. And then H minus 1 Q is H1 dual space of H1 0. Okay, maybe next week, I want to start to prove this. Thank you very much for your attention. Today I want to stop it.